I'm Darren Martyn. I'm here to talk to you today about process injection for everyone using Python. And yeah, so I'm also go by the name of infodox. Some of you I know from Twitter and such like. Some of you I've never met before, and lovely to meet you all. Work at Cyphers Research down in Birmingham. We're a small boutique penetration testing company, and also happen to be a forensics chemistry student. So I'm not really from a programming background as such. You know, I come more from a sciences background. So, you know, I mean, this is kind of aimed towards, you don't really need to know how to code and such to kind of keep up with this. You know, I'm going to kind of step through it as we go along. So yeah, what we're doing today is we're discussing stuff like memory resident processes, backdoors, manipulating what another process is doing in memory, you know, messing around with it, you know, not just debugging it, but manipulating what it's doing at runtime and basically altering its state. And we're going to be doing all this with Python, as opposed to, you know, lower level languages such as C or assembly, which is the norm for this. But this, you know, this kind of stuff is useful for a whole bunch of stuff. I mean, say you've got a piece of malware, and it's using one of these runtime packers that, you know, we'll say UPX on steroids, use weird encryption stuff. You use the kind of thing to take it apart, you know, and debug it at runtime and dump out the code that you're looking for. Or, you know, cheat in video games. Any play games? Yeah. You know, I mean, you know, you can add like wall hacks and such, like Counter-Strike, all that kind of fun stuff. You do that by modifying the memory of the game, and also stuff like extending a program, you know, patching it at runtime and such like, and developing what we call forensically challenging code. Stuff that's a complete pain in the arse to figure out what it's doing. You know, making it difficult for people like Dave over there. You know, making his life a bit harder. And hopefully we'll make it a bit easier later on.
It's more fun that way.
Because today we're going to talk about, we're going to be bad guys today. Instead of, you know, cheating on a video game, we're going to develop some really sneaky malware that doesn't have files on disk or its own process in memory. It lives inside something else, like a parasite. And to quote favorite character, Firefly. So, forensically challenging malware. Most malware drops from disk, you know, registry keys, you've got files, you've got distinct processes, you can see it. So today we're going to talk about something that's a bit different. It doesn't have a file on disk, it doesn't have its own process, it's invisible. Not impossible to detect or to mitigate against. There's ways of stopping this, there's ways of seeing it, you know, there's ways of going, hang on, what's wrong with you? So, you know, you can definitely detect it, but it's painful, it's difficult. We're going to discuss how to make it, and then hopefully how to go find it, maybe. So first off, because we're messing around with process memory, we need to know how the stack works, because, you know, what's in a process memory, you know, how does code run? So I'm going to give a quick and kind of terrible overview of the x86 stack. It's not going to be too in-depth, because we're only looking at a small bit of it. Most of you know, you might know it, you might not, but you know, there's somebody who doesn't, so 32-bit on x86, these are registries. We've got EAX, ESP, all these registries. We don't care about most of these. We care about this one, EDX, and EIP. EIP is the important one. Extended instruction pointer. That points towards the next bit of code to run. That's like, in exploit development, such like, that's what you care about. The rest of them, not so important. So here's the stack. It goes this way. You got, you know, memory going, you've got memory in the stack, and it goes up, and it's called stack because stuff goes on it and then it gets popped off it. You know, it's a bit like in a restaurant, you got, you know, stuff stacked. I mean, computer people, they weren't very imaginative. They kind of named things, you know, a fairly simple way. Now, the IP, for anyone who doesn't know, is the extended instruction pointer. It's placed in the stack where the next bit of code to be ran sits. You got the next opcode to execute. When you're writing exploits, normally what you care about is when you're messing about with the debugger or something, you see 0x41414141 on the EIP, you're like, hang on, that's code execution. That's what you want. You care about the EIP because that's, you know, you've got control over what codes run next. Conceptually what we're doing is similar to writing an exploit in that we need to control EIP, but, you know, we don't have to actually exploit a vulnerability to do it because we've got debug access. We can just tell it, run me next. So it's, you know, it's a bit easier than writing some really deeply technical exploit. So yeah, instead of triggering an exploit, we're using ptrace. Ptrace on Unix is process trace, the syscall, which allows you to hook a process, read-write memory and such like. You can, you know, get in there, mess around with it, and, you know, dump it out and such like. And yeah, it's like GDB, debugging software, they all rely on this ptrace syscall, and we can modify the stack. You know, we can do whatever we want basically once we have debug access. So how does process injection work, which is what we're going to talk about today, now that kind of cover the stack a bit, not too in depth, but yeah. Basically attach to the process, go, that's the process I want to modify and manipulate. We pause it, you know, to keep it in a suspended state. We get the instruction pointer, EIP or RIP or PC, depending on your architecture that you're working with. We override it with shellcode, our program code and assembler that we want to run. We set the EBX or RBX, depending on, again, which architecture, R1 and R, as I only found out the other day when I started messing with it. And then we just go continue, and then our shellcode runs, or so we hope. So, wrong thing. Is it this easy? Maybe, maybe not. It's been done before. I'm not talking about anything new today, per se. It's been done before, you know, it's been done before with Simon. Been done, written in C, was published in Frac. For those of you who don't know, it's a scary hacker magazine full of awesome stuff. And it worked on x86 Linux, and it was really effective because it was really slick. Problem is, again, written in C, not the easiest to understand. There was also good stuff done in VX7, published on a virus writing website by a guy called Elfmaster, who's an absolute bloody genius when it comes to this stuff. libhijack by a guy called Latera. It's a whole library for hijacking other programs. There's Parasite by Jack the Ripper, and that's a really simple C implementation, which just, you know, it's kind of a reference one for it, and it does the exact same thing. None of these though, all these are C and assembler, you know, they're, you know, low-level languages, they're hard to understand. Yeah, they're just painful to write in. This is all you have to do in Python. Attach, get instruction pointer, overwrite, set the register to 0, carry on. It's, what, 5 lines? I mean, I bet, you know, kids over the kids track probably write better than that. They probably do it in 2. But you never know. Yes, this demo was going to be live, except my laptop kind of, you know, went haywire and doesn't work anymore. So I recorded it at work yesterday, and well, you know, it's not as fun as, you know, actually doing it live and having to fall over a few times. But yeah, it's unfortunately pre-recorded. Okay. Where do I leave VLC on this thing? Probably open file, there we go. This is a demo on 64-bit Linux, and what we have here is we run a program called test, right? And test is just, it simply sits in a loop, it prints out its process ID once and then just endlessly loops. It's just to sit there, it's a demo program. And then we run the simple injection program, the one I just showed above. It attaches, it does all that in seconds. You know, there's no real, you know, you might shave a few seconds off your writing in C, but in Python this just does it really fast. And all of a sudden, you know, it's injected our shellcode. Our shellcode now lives inside test, which you can see test is still running. And now the shellcode we're using is a bind shell at 4444. And as you can see, you know, we've got this bind shell and it kind of works. Of course, the problem is, watch closely now. See, test there has gone and quit. Our shellcode crashed the process after it exited. It didn't return cleanly. So, hang on. So yeah, just, you know, it's just kind of we're going to stall for a minute. So you've seen how it works. You know, it works, I hope. You know, anybody, you know, just to, because, you know, some people, they don't, you know, they don't speak assembly too well or whatever, you know, everybody all right with so far? The concept per se? Any questions or such like? You know, I mean, we've got the stack. I mean, you know, some people know, some people don't. I personally didn't until a couple of years ago. I kind of pretended it didn't exist because it was scary in assembly. I was like, no, I'm going to stick with my SQL injection because lol PHP. You know, but you know, it can be a bit alien for some, you know, and any question just ask throughout, you know, or any abuse, heckling, go for it. Especially abuse, that's fun. So, problem. As you saw, the host process, the one we were injecting into, it crashes. And if it doesn't crash, I mean, a couple of times where it didn't, but just started acting really haywire. Like I had one time when I was testing it, and it just started spitting out, you know, started spawning bin sh. I was like, what are you doing that for? You know, just because something went weird and wrong. And so this is, you know, it's hideous, it's ugly. I mean, if you do this on a box and you crash the process, say you inject into Apache or SSHD, and next thing SSHD falls over, admin's going to be going like, hang on, where's my web server? Where's my remote, you know, what's going on here? Somebody's going to get really annoyed and you're going to get picked up. So what do? So that was doing it wrong. That was making a mess. So we need a solution to this. We need to find a cleaner way of, you know, we've got the injection working, but we don't have, you know, everything falls over straight away. So, you know, what do? We've got our code running in the infected process, which, you know, that's a start. Our code's now invisible. We need our code to, you know, not muck up the process, not make an absolute haze of it. So we need to run alongside, kind of in parallel. We need, you know, it running side by side in harmony, and, you know, everyone's happy and such. So how do we do this? Well, we level up a bit, we swear at the computer a few dozen times, and then we think, how about we just fork it? So we prepend our payload with some fork shellcode. Process forked, new clone runs, and the original process we hope to God kind of runs unchanged. Maybe. Sometimes it, you know, we hope it works. So for anyone who's, you know, who isn't familiar with what fork does and such like, it's not just a thing on GitHub, but it's the same concept. Prepending means we have fixed something ahead of it, ahead of our original payload. And the fork syscall, it creates a new process which is the exact same as the parent process, it creates a child. This helps avoid, you know, messing up the parent process because we inject our shellcode into the child after forking the parent. And this is where it gets really weird, you know, to actually visualize. So you've just made one into two, you know, put bad code into the second one. And hopefully the parent process runs unharmed and everyone's happy. So to do this, we prepend our shellcode to our shellcode. This is where this actually got fairly difficult from the start. And step one, fork, step two, run. And of a really, really awful picture somebody redrew for me at the last minute. So yeah, you've got parent process, and then our fork shellcode goes in. We've got parent process carries on, and then the child process spawns the shellcode in. So the child process is affected, it's got our nasty code in it. Our nasty code doesn't own its own process, it's inside this other one. So, you know, theoretically invisible, but somebody might call me out on that, might go, no it's not, I've got a thing. So, yeah, this is another pre-recorded, unfortunately. I planned to do this one live, but, well, laptop dead. So, yeah. Let's see, where are you? Videos. There we go. Is this? Okay, there we go. Thought it crashed or something. So we run the test program again. You're going to see this test program pop up a whole bunch of times. And yeah, we run the prepend fork variant of it. This is like a second, this is like version 2 is in. I hope I don't, you know, ruin everything this time. So the prepend fork variant, it avoids killing the parent, but it forks it to the background, unfortunately. So it didn't work out too well. I had it working, then I went to record it, and you know the thing with demos, you know, everything goes and kind of falls over at the worst time possible. So we've got our shell again. And yeah, that actually did work in the lab, kind of. This is the way it is with demos and such like. So with fork, we've created a new process that shows up in process listings. So say you run PS or top or whichever, you know, whichever your preferred process viewer thing is, you're suddenly seeing that, say you've got 2 SSHDs now. You might notice, you know, it's problematic because you're not living in 1, you're now living in 2. In future, there's clone syscall. Now, I couldn't figure out how it worked properly. I tried, but Simon Thor does it on x86. when I tried to port that to x64, it just fell over and crashed everything. So I kind of just gave up, went, come back to you later. You know, maybe a bottle of scotch and sit down some evening and go, work, please. But yeah, kind of gave up on that one. So back to Python. You know, we've kind of looked at the base, you know, the base of what memory injection is. So, you know, why aren't we doing this in C or assembly? Why aren't we writing a shellcode that does this? Or, you know, why are we doing it in Java? You could probably. I don't know why you would, but Python, because it's simple. As you saw earlier, it's like what, 5 lines of code. So the injection code is really short, and we can easily improve it if we feel the need. We can make it more reliable. We can make it more robust, more portable. We spend more time working the rest of the project, like the hard bit's actually writing the shellcode to inject. You know, you spend maybe 10 minutes writing the Python bit, and then like 2 weeks writing a really, really solid shellcode that does something really cool, like, you know, Jacob Applebaum. You can annoy him by writing one that does RC6 encrypted reverse shell over UDP, and he'd freak out and think you were the NSA, if you were so inclined. It'd be funny, and a pint for whoever does write some shellcode like that. So we've got our injector, and it kind of works. And now this, just a forewarning, unfortunately no demo here because I forgot to record it and my laptop's bust. But yeah, there's probably a side that goes demo, and we're like, hang on guys. But yeah, we haven't actually fixed the stack. We've left the stack all wrecked. You know, we've shoved our shellcode in, even with the fork prependered, and you know, we've just kind of left it in a state. So yeah, it's going to crash, it's going to fall over, it's going to behave really oddly. So in the next bit, I was going to attempt to restore the registers after injection. Unfortunately, demo's not working out, but so far I haven't made this work flawlessly. It does fall over a lot. So it's a bloody minefield. Somebody else figure it out, fair play. Unfortunately, I'm not quite that, you know. So yeah, restoring the registers. Again, this crashes, you know, all I did was I saved the state of the stack pre-injection and then kind of restored it using setreg. It was filthy and nasty and it crashed half the time, and yeah, I'm going to skip this bit because the demo doesn't actually exist anymore. So yeah, swiftly on from that. Because Python, it doesn't matter what we run it on. We don't care about the operating system or the architecture. Python will run on anything with a Python interpreter. OS X, FreeBSD, OpenBSD, Linux, even Windows, if somebody installs a Python interpreter, you can do this kind of stuff. It doesn't matter about the architecture, you know, ARM, x86, MIPS, x64. Yeah, it's an interpreter language, so we can write once and then go and own everything. So the next thing I wrote was process injector. It automatically would determine, am I on 32-bit or 64-bit, you know, to figure out, you know, what am I running? It'd select the right shellcode to use the right injection technique, and then it'd use that to pop the box. Now, so, you know, we could write like a detect architecture, and this was 2 lines. Well, 3 if you're going to count the print. But yeah, import platform, and then RT equals platform.machine. 64-bit, 32-bit, magic. So, porting this to x86, we've been working with x64. We've got 2 steps. Hard part, rewriting our shellcode for 32-bit. That takes most of the time. And the easy bit is rewrite the injector part. And porting the injector, which was the Python bit, is literally like replace RIP with EIP and RBX with EBX. When I sat down and did this, I was like, this can't be this easy. You know, no, why? And then I realized it's actually really cool. You know, I can just literally add a new architecture with like 2 lines of code. So, you know, you just swap out the bits and, yes, sort it. So this is the same injection code running on 32-bit. Not live because the laptop I brought with me again, yeah, I feel a bit silly about it falling over and dying on me, but what can you do? We can open file, 86. This is the same injection code running on a 32-bit box. So we run our test program, and then we check, and those are the ports that are listening after running a test. And then we run our injection program, and then we check the, you know, what ports are listening. Again, we've got this one here, 64533. You know, what lives in 64533? Oh look, you know, it's a magical bind shell. you know, suddenly, you know, it actually worked. And this is like 10 minutes, and I was like, oh, this is really easy. You know, it's like, this is, you know, way simpler than if I wrote this in C and I have to compile it for different architectures. If I wrote it in Java, well, you know what Java VM is, you know, you've got like, oh, I'll work on this version, you know, JRE 1.6 point whatever, but, you know, not 1.6 point whatever else. But in Python, just runs on everything. So, x86 and x64, they're, you know, they're well documented, you know, people have been playing with them for a while. You know, everyone's, you know, kind of messed around with 32-bit, 64-bit box, because that's what all of our desktops, you know, and our laptops are. And then realized I could run Linux in a CH root and an Nexus 7, which I picked up. And I was like, this runs ARM. Can I do this in ARM? You know, I've got Linux in it. So, you know, let's go take a look at ARM for fun. And this was, I think, Tuesday night. I kind of, you know, I decided, hang on, I'm going to add a new architecture to this because, you know, I've got this tablet thing and I've got nothing better to do. So, on ARM, the extended instruction pointer, or EIP, the one that we're interested in, is known as the PC register. Program counter, because RISC architecture is amazing, and it's like, reduce everything and make it so much prettier and easier to understand. ARM is lovely and elegant. So our EBX equivalent is the R1 register. Don't know what R1 stands for, doesn't really matter, register 1 or something, I guess. And the other registers, you know, we honestly, they don't matter. We've got PC is the one that really matters, and R1 just kind of matters to make it work. The others, it's RISC, you know, it doesn't really matter. So, first attempts were massive failures. The injection was working, you know, I was injecting the shell code, and then everything would fall over, and I'd be like, what went wrong? You know, why is this crashing? And apparently my shell code was too big to actually fit on the stack. It was just clobbering everything. So, yeah, it was causing seg faults, which most people probably know is a crash. It's bad, it'll trigger alarms, you know, you might get core dumps everywhere, and the admin's going to go, why is everything crashing? Now, if you have an admin in an ARM box, that's a bit far to, you know, I haven't seen an ARM actual server in the wild. Maybe somebody's Raspberry Pi, but I'm not an expert at ARM. I like it, you know, it's fun to play with. I'm not going to, you know, spend too much time studying it yet. But it seemed that, you know, my massive, bulky, hideous blocks of assembly shell codes were, you know, clobbering everything, ruining it, and it was falling over. So I ended up using a staged Metasploit payload, which I felt a bit dirty about because, you know, using somebody else's code. So yeah, no pre-pen fork yet. And yeah, it actually worked. After like a few hours, I suddenly had shells appearing on this ARM box, on, you know, this tablet. And I was like, oh, you know, this is actually really super portable. You know, we don't just have it running on, you know, on desktop types. We can now just do this to a tablet or, you know, a Raspberry Pi or some embedded weird device like, say, a router or a switch, which is so much cooler. So yeah, we actually got it to run. So after, you know, having a look at process injection, you know, writing a bunch of scripts to do this on different architectures, I started thinking, you know, I was looking back and I was like, well, we can, you know, how about one ring to rule them all kind of thing? One script that does it all magically for everything? So, you know, why don't we just automatically detect which we're on and then, you know, inject into all of them? So, wrote this, and using the typical, you know, the now traditional NSA ridiculous naming scheme, call this diabolical mouse, this really, really awful piece of code that it just runs Python code in memory over SSH, just kind of for demo purposes and to mess around with friends and people. And I decided to test this to see if our cross-architecture injector thing, I'm not quite sure what to call it yet, it's more of a, it's not even a proof of concept, it's like a monstrosity of Python. I mean, somebody's going to call me out and go, mate, your code's rubbish. They could be like, why are you doing this? And I could be like, oh, it worked at 3 in the morning. So yeah, I decided to see if we could get this to work without writing a single file to disk. It kind of works. And yes, the injector tool I come up with a suitably ridiculous name of Enchanted Mushroom for, because you know, this whole naming scheme, you know, we're going to stick 2 completely unrelated words together and go, this works. So yeah, again, pre-recorded, because there's no way I'd be able to bring 3 boxes with me and get them all to work simultaneously. So yeah, file. There we go. So we've got our Metasploit listeners running, all three of them, and then we run it against blindly. We don't know what architecture any of the targets are. Our scripts just get blindly fired at all three of them in hopes that it works. And yes, I like colors. Yeah. So suddenly, we've got all three shells. It's automatically detected which kind of architecture it's on. It's ran the thing, and yeah, we've got the ARM box popped. And yeah, as you can see, like there, it automatically detected 64-bit. It detected ARM. Further up and scroll back, it detected 32 bits. This was completely blind. I didn't know which box is which. I just put the IP address into the targets file and went, they're on the network, have at it. This is done, no computers are harmed in making that, by the way. That was all, done inside a test environment. So, yeah, as you can see, it, blindly and automatically, it just owned them all. Now, yeah, that's a quick note, by the way, we did need credentials for that. You could add in a SSH brute forcing function or some kind of magic there to crack passwords and do evil stuff. There'd be like an extra 3 lines on the actual Python, on one Python scripts. But we just because we're not writing this for malicious purposes and we're being nice and all. So future ideas will be to explore this further at OS X. I know it can run an OS X, but I don't have a MacBook because it kind of blew up. So yeah, I got this MacBook and it decided to stop working with making loud noises, so I haven't been able to explore that. I know it can work on BSD. The library I've been using, Python ptrace, works on BSD, OS X, Linux, not Windows. Windows doesn't have a ptrace syscall. It does have the Win32 API though, and you can use create remote thread to execute code inside another process.
Solaris.
Which Solaris?
It probably will.
It probably will.
It's fine.
Yeah. Yeah, Solaris is ptrace, right?
Yeah.
Yeah, Solaris would be fun. Yeah, so automatic OS detection, you just have one script that's like 1,000 lines long and has every operating system known to humankind in it and every architecture. And then, automatic OS detection maybe. More architectures, MIPS, little endian, big endian, Spark, PowerPC, what have you, all of them. This stuff, we can do it anywhere basically, so why not explore, branch out further there? There's some, you could have this run on switches, routers, and other really shiny embedded gear. How about improved shellcodes? Like how about, a shellcode that just runs and does nothing, and then like a port knocker, for example, you send it a few packets and it sends you back a reverse shell, or the one to troll Jacob Applebaum, which somebody really has to write. It'd be really funny. How about we just remove Python ptrace entirely, because that's not a standard library. So we can implement our own ptrace using C-types. C-types, for anyone unfamiliar, C-types is like Python's bindings to C. So you can like access native syscalls and such directly without mucking about with having an extra module. You can do weird stuff like directly access memory through C-types, but it's a bit of an ugly interface as is. Or stuff like, instead of having to write a shellcode, how about you just inject a whole ELF file? You can just go, right, in goes nmap, I'm running nmap inside SSHD. Why not? The barrier of entry is very low. I mean, I started playing with this a short while back and I got it to work overnight. Anyone can mess around with this. You can do some other really cool stuff, like I've seen some guy wrote a thing that it hooked onto a process and started fuzzing it in memory. You just started mucking about with it, see if you could find crashes that way. You can write a debugger. You could say have your own implementation GDB in Python if you're so inclined. I don't know why you want to do that, but yeah. Limitations though. As an attack vector, as the attacker, you have to already be able to execute code. This is a really important point to know. If I can execute code in your box, I can execute code in your box. This means, by the time the attacker can actually use this kind of bad stuff, to do evil, nasty things, you've already been popped. As in, somebody's already, you've got weak credentials somewhere via, say, SSH, or maybe you've got vulnerable software running and somebody's popped a shell that way, etc., etc. This is post-exploitation. It'll not gain any further access, it's not going to give you extra privileges, it'll keep you in the system. And the cool bit is when they unplug and plug back in the box, or suddenly all the evidence is gone. You don't live on disk. Forensic people, I know there's at least one in the audience. Is there any other forensics people here? No? Okay, they should be, they should be aware of this, because a lot of analysts, they'll just, like when I did a computer forensics course, recently, there's like, oh yeah, you just, you pull the plug in the box and you just analyze the disk. But, you've just blown away all the evidence. Where's it all gone? Well, oh, I unplugged the box. So, some analysts that only look at artifacts actually written to disk, they won't look at RAM. That kind of analysis is useless, because unless you're lucky enough to get it swapped out to disk and, in the swap partition or something, you're not going to see it on disk. It just isn't there. So, you should always dump the RAM if you suspect, a box has been compromised. You dump the RAM and examine that, because, somebody could be using this type of stuff to not live on disk and live in memory only. So, you dump the RAM. And, if you did that, I'm not quite sure how you'd spot it in RAM. I'm not, an expert at it. Would you compare it against known good samples or something to spot the difference, or would you just sit there and go, where is it? I'm not 100% sure of that, but I suppose you'd have to compare it against a known good sample of memory. Anti-malware solutions, they should, actively scan memory, might defend against this. I mean, most of them don't. They just, I think, AVG, does that like scan memory now? Anybody familiar with any identifiers that actually check memory?
Most.
Which?
Most. By ESET will.
ESET, yeah?
Yeah.
Oh, so I'm not too familiar with AV products, but I assume if they scan memory, they would pick up,
ESET will, this person will. AVG should shit it, so.
Kaspersky does though, yeah?
Yeah.
Oh, okay. I'll make a note of that, because, I was wondering how would you pick up this?
I've always had it pop up on stuff on this.
Yeah?
So.
Duly noted then. Network forensics maybe, you might pick it up, the actual payload going across the wire. You could detect the attackers going down, you'd see the weird blob of Python stuff going over the wire and go, you're not right, and then you'd actually have my code and you'd be like, well, it's not written to disk, but it's on my snort box. Maybe that'll help, that'll tell you at least, when it happened, I guess. It might tell you there's something weird going on, like a bind shell opening up, hopefully. Possible mitigations, actually ways of preventing this, stopping it dead, stopping people doing this sort of stuff cold. You could simply stop access to ptrace as a syscall. You could just patch the kernel and go, no, you're not allowed that. It's a bit silly, you wouldn't do it in a development box because you can no longer debug anything. It is doable though. Some distributions take this approach by locking it down. They make it inaccessible to non-root. But they do it badly, and there's workarounds for bypass. Ubuntu kind of does it. It won't allow you to ptrace anything but your child process, unless you're root, which basically ptrace everything. Disable it entirely. You could just remove it. You could just actually patch the kernel, or you could, limit its capabilities. GeoSec locks down ptrace fairly well, but it's been shown to be bypassable. Don't tell Spender, he'll go ballistic. But monitor process memory, I guess you could, monitor stuff in, what is it? In dev you could monitor, process stuff in there, and proc mem, stuff like that. You can monitor that, and if you see something getting mucked about with, you could, flag on that. You've got host-based IDS that might do that. In summary though, Python makes hard stuff like hacking memory. It makes all this really, really easy. You can write cross-architecture in-memory malware. The shiny term these days is implants. I don't know why. It makes them accessible to everyone. A 12-year-old could write this in theory. If a 12-year-old was given like, here's how to do it, your average 12-year-old would go, right, here we go. There's, your super evil malware stuff. Most architectures, like I did 3 in total, I'd say, on the first one down. Very little effort, very little modification of code. You could add PowerPC to my code in like 2 minutes, I reckon. If you're familiar with it, which I'm not. I'm not a PowerPC guy. I don't understand it. It's strange. It runs on old Macs. It's a pretty weird architecture. Anyway, further research is needed into actually forensically detecting this sort of thing, because I haven't seen any defense stuff written about it. I've seen a couple of offense things going, well, here's one in C. But I've never seen anyone going, here's how we stop it, here's how we detect it. I think Kaspersky actually did once detect in-memory malware. Some Russian guys used a Java exploit that simply ran Java code in memory on some website to rob banking credentials or something nasty like that. And that was the only time I've ever seen in-memory stuff flagged in the wild. So, there's further research there, and if somebody comes up with a solution, well, fair play to them. And yeah, actually, we ended up fair bit early, but yeah, thanks to the organisers for actually having me here. Thanks to my co-workers for helping me get this off the ground a bit. Now, unfortunately, because demos failing and such, it's a bit shorter than expected, pre-recorded stuff. But and yeah, thanks to all of you for putting up with me for however long it took. So any questions, abuse? Yeah.
So looks like a job for volatility, isn't it?
For which?
Volatility, the RAM for
yeah,
tool,
that's what I reckon it'd be. You could, if you got a RAM dump, you could examine it with volatility as what I think could be the way forward. I still need to examine that a bit. Like I'll have to RAM dump a couple of VMs and play with it.
Yeah, I think I'll go with that as well.
The code, by the way, will be published Monday or Tuesday. I just want to clean it up a bit, make it presentable and pretty for the world. It will come with all the flashy, blinky lights and tags, by the way, because, code that doesn't blink and flash,
So I think you made a really good point. You talked about network forensics as well, because it's something that a lot of organisations frustratingly are sort of turning away from now. And they're going, SIM, it's all about SIM, look at the logs, check the logs will tell us everything. And it's just not, it's not true. And I've had this argument with the companies which I won't mention the name of, and they're just totally moving away from the whole source file snort boxes, security onion. It's sort of getting pushed to the side, and this is a good reason why it shouldn't be.
Because this,
this with your SIM. If you want to use SIM, fine, but use
it complementary. As like with your network forensics box, you can use that to complement your logs. Because if you see something that doesn't correlate with your log files on the network, in your snort, and then you've got your logs on your host-based stuff, you can go, wait, why is there disparity? Because that's when you find a breach. Whereas, if they're just chucking out that and they're going with the latest shiny, FireEye boxes or whatever it is these days they're playing with, you're going to miss a lot of stuff because you're, as you're saying, it's a bit annoying. They're kind of blinding themselves in a sense.
Suckers for the vendors, aren't they? That's the problem.
Yeah.
Believe what they tell them.
Any other abuse questions? Yeah?
Can I implement C-types on it?
I'm going to be doing the C-type variant.
So what benefit rather than using like outside? Because you sort of bring your C into the equation and you want to go away from using C?
It's the only reason I'm implementing ptrace in using C-types is to remove the actual Python ptrace dependency, which is a third-party library. Every version of Python shipped since 2.5x has had C-types built in. So if I write the library once, you can run it anywhere. And I've sat there and I've gone, should I do it? This can be painful and take about 2 days to write. Might as well. I've seen a couple of implementations that are really hacky and nasty and huge. So maybe if I write a really small one, you can just drag and drop in. Maybe somebody will find a use for it. Easy ptrace.py or something, or tiny, or some kind of shiny name for it. I can see where, why would you go back and write it in C?